Okay, good morning. Happy Monday.
Good morning.
Professor, before we get started, I have a quick question.
Sure.
So for the homework that's due tonight for the problem 2, there's a couple of times, I don't know if I'm reading the table wrong, but I'm going on the table and the boxes are empty. So like there's no reduce or shift or anything like that. In that case, do I just push the symbol onto the stack?
If you ever come to a place where you're having an empty box on the table, then something isn't right.
Okay.
That's like the automatic reject case.
Oh, okay. I understand. All right.
Okay.
Thank you.
So hopefully the string that I did never puts you in an empty box if the rules are followed.
Yeah, I probably did something wrong.
Well, I'll say the same thing. I'll probably did something wrong. So if I did, I'll hear about it. Someone asked a question about that. Oh, about the lecture from Wednesday. I had neglected to post on the Canvas page. I have them on YouTube, so that's normally my process, is to put them up on YouTube, and then I link to them to this page. So if they're missing, you can always try my YouTube channel. And then if they're still missing, then it means I've dropped the ball somewhere. Also, partly because of that, and partly because I think our poor homework grader is still struggling to keep caught up. I've gone ahead, I've moved this to Wednesday. So if you all have some more questions, you can ask them in the discussion section of the Canvas as you're working through it. So for those of you, if you've already submitted something and you want to resubmit, that's fine. But don't worry about this till Wednesday. And moving on to this week's topic, we're still in compilation. So we're going to do compilation for 3 weeks. The first week was about syntax and parsing. Excuse me, this week is about semantics. And we are going to take a very shallow dive into a very deep pool. So I'm going to put these notes online. And I'm also going to put several book chapters online that deal with semantics. And I just need you to get a top view of this stuff, basically to understand what semantic analysis is trying to do and what the major ways are of completing it. So it's not going to be quite as detailed as what we did for the syntax processing. And the same is going to be true for the next week, which is optimization. Optimizations are pretty well known, and I'll cover some of the basics, and then again, the idea is so you have an understanding of what's happening during compilation, not that you become a compiler expert, although you never know where your career will lead you. Okay, so here are the outcomes at the end of the week. Go back and see if you've gotten them. And this is the slide from last week, different phases of compilation. And here we are, we're in semantic analysis. So the main thing with semantic, again, you guys know the difference between syntax and semantics, right? So in syntax, what are we talking about? What are we talking about? What would be a good way to distinguish syntax from semantics? Either in programming languages or natural languages. What's a good definition for syntax?
Syntax would be like the rules that you follow, sort of the grammar to determine if the string is in the language.
Exactly. So syntax is all about structure. And what is semantics all about?
semantics is more about like the meaning of the code, right?
Exactly. And in a natural language, the meaning of a natural language sentence, but also the meaning of the code. Now, what do we mean by the meaning of the code? The standard definition for meaning of the code is observable input-output behavior. Think of, I think all of you guys have done some black box testing at some point. If I were to give you two computers running code and I said, I don't know if I'm running the same code here, and then you just started poking it, you started putting in inputs and watching the outputs, the observable inputs, the observable outputs. And if it was the same on both machines for both pieces of code, you would say either they are running the same code or they're equivalent. So we could ask the question, are these two programs equivalent in behavior? And what we mean is, for the set of all possible inputs, do I get the exact same correspondence between input and output for those two programs? Why can't I just write a piece of software that scans the code of both programs and tells me that they're the same? I mean, if they're literally the same piece of software, we can do that, right? Because we can just check line for line. But what if I wrote program A to do a job and you wrote program B to do a job? Why can't somebody else just write a piece of software that takes in both of those programs and says, yep, those two programs are exactly the same? It doesn't execute them, it just analyzes them.
It's hard to interpret the meaning of those programs.
Yes, that's right. It's hard to interpret the meaning of those programs. Do we have any kind of formal statement about that, how hard it is to interpret the meaning of those programs? See, this is the impact of what Alan Turing said. This is what Alan Turing's, the Church-Turing thesis is saying. It is not a decidable question. If I take program A and program B, and then I write another piece of software that scans them, does not operate them, but scans them and analyzes them, and then I ask the question, are these two programs equivalent in their behavior? In other words, is this input-output behavior exactly the same? And the answer is yes or no. It's a decidable question, or it's a decision question, I should say, but it is not a decidable question. And it goes right back to the halting problem. Run this program, even the question of, can it halt? So when we were saying earlier in the Turing machine module, hey, we're going to take a Turing machine and feed it into another Turing machine, that's the theoretical equivalent of saying, in the real world, I'm going to take a piece of software and feed it to another piece of software as input. And then that other piece of software is going to tell me about the behavior. And you can say very, very, very little about the program behavior. So syntax, going back to this, is about structure. Semantics is about meaning. And we are frighteningly limited in what we can say about program meaning and program behavior. And again, you know this intuitively because you've all spent a lot of time writing requirements and tests. And if you didn't have to, if you had the ability to not do testing, but just prove program correctness, prove program behavior by analyzing it with another piece of software, that's what you'd be doing. The fact that you're testing is proof that this is a non-Turing computable problem. So what this module is about is to start to talk about what can we do in terms of the semantic analysis. And it is quite limited. That doesn't stop this from being an integral part of compilation, because it turns out some of the simpler questions that we normally can answer, not always 100%, but that we normally can answer are important, like type checking, like initializing variables before use, things like that. All right, let's look at syntax for a second. that a syntactically valid sentence? Yes. Is that a syntactically valid sentence? Yes. Hopefully you're saying yes. There you go. Now, the first one is semantically valid also. I am saddened that it's not true, but it's a semantically valid sentence. And the second one is not a semantically valid sentence. So we can have semantical nonsense in syntactically correct statements. Now, the thing about natural languages, though, and this is just a brief aside, is it gets weirder than that. There's some famous examples that a guy named Vinograd did, I think, in the 1970s. This is one of them. This is one of them. I'm not going to spell this right. There we go. Here's the problem here. In natural language, syntax and semantics are actually tied up with each other. They're inextricably bound. And so when you're parsing this sentence, he saw that gasoline can explode. What's the role of the word, if we're going to lex this sentence, what's the role of the word can? Is it part of a verb phrase, can explode? Or is it part of a noun phrase, gasoline can? And the answer is, we don't know. So the semantics of the word can and the syntax of the word can are inextricably bound. Now, how do we resolve that? Well, when you're just given one sentence like that, you don't resolve it. So how do you normally resolve it? Context, yes. And yay, we're back to context. We're back to context grammars, right? Unrestricted, context sensitive. So if I did this, now, oh, okay. Now I have a stronger sense that gasoline can is the noun phrase. Syntax and semantics are bound up here. Whoops. The chickens. Are the chickens the subject or the object of that sentence? In other words, are they the actor or are they receiving the action? Are they eating or being eaten? And again, the semantics and the syntax. If you syntactically parse it one way, you get one meaning. If you syntactically parse it another way, you get another meaning. And sometimes I think there's here the syntactically, it's the exact same. Every parse is the same, but we still don't have clear meaning. The semantics is unclear. We don't know if he's already met a Norwegian and wants to propose to this person, or if he's on the hunt for a Norwegian that he hasn't met yet. So we deal with this every day. We're good at dealing with ambiguity. How do we avoid this problem in programming languages? question, right? We've all read a programming statement, maybe that a friend has asked us to look at. My program doesn't work. Would you look at this? And you look at it and says, I have no idea what this means. I have no idea what you're doing. That's just bad code. But if you look at a single line of code, syntactically, can you parse that line of code? And semantically, do you need to know what it means? Can you parse that line of code? Can you lex it and say what the role is of each part? The role of X, that's a variable, right? The equal sign is the assignment operator. Foo with the parens, that's a function call. We know the role of all of those things. Do we know what X represents? No. Do we know what foo does? No. So what's the difference here? Programming languages versus natural languages. The difference is programming languages, being formal, have rigid syntax and then have unambiguous rules for what the operations are that are being requested. That's the big difference, which goes back to a previous theme. Computation is a mindless exercise. It is a mindless exercise where you are manipulating symbols using well-defined, unambiguous rules. That's what computation is. And it has no inherent meaning. And so that's the thing that allows the mindless computer to do it. Now, what that means is we could do our syntactical parse completely separate from the semantic parse, and we cannot do that. We cannot do that in a natural language setting. The reason is, although technically speaking, chickens is a set of symbols that has no meaning, in the context of writing that sentence, the word chickens absolutely has meaning embedded within the symbol. If I think of the word chickens as one symbol, it's embedded within that symbol. And we cannot pull it out. But here, there's no meaning embedded in that X, so we can do this separate. All right. So syntactical analysis can be done. The only reason we can do syntactical analysis at all on a programming language is that we have well-formed rules through BNF grammars that are unambiguous and formal in the mathematical sense, so that there is no choice allowed in the lexing and parsing. And we're very good at it. The semantic analysis, what does it all mean? Well, we don't know what programming, a program means. It's very difficult to talk about the meaning of a program other than input-output behavior, but we can do some kind of mini meaning things. And the main things are things like type checking and maybe in some cases, some limited cases, you can do loop termination. You can do variable was declared before use, variable was initialized before use, things like that. Those are actually non-syntactic questions. Sometimes we can answer them in a syntactic way, but they're really non-syntactic questions. So what we're doing is just getting a top level view of this stuff. Now, some people actually try to go deeper just before I go on. I did see a really interesting talk where at Embry-Riddle, a guy came and was talking about how their company is creating software to analyze other software to try to determine if the other software is a virus. And he admitted freely, look, this is not Turing computable. We can't do it all the time. But the current way that people check for software for viruses is syntactical. They look for pattern matching. And the way that virus creators get around that is they basically obfuscate their program. They put in random, meaningless, non-executable statements. They put in random, meaningless loops that don't really change anything or do anything, but it breaks up the syntactic pattern. And what their software does is tries to remove all these things and basically normalize and de-obfuscate the code, and then look for patterns of behavior, input-output behavior, or register allocation behavior, or memory access behavior, indicative of things that are suspicious, fishy, and virus-like. And he admits, okay, we cannot do it in the general case, but we can often catch, based on behavioral examinations, that this is most likely a virus. I thought it was fascinating talk. Okay, so here we're talking about program behavior. Like I said, this is a brief overview. I'm going to give you not just these notes, but some book chapters. And by all means, if you want to read through the book chapters, that's fine. Unfortunately, a couple of them, it's really about segments of the book chapters because they have a lot of other introductory material that they rely on that you don't have access to. If you want to get a good book on this whole course topic, there's a book, it's called, well, it used to be called The Pelican Book. I don't know its real title. It's The Pelican Book because it had a pelican on the cover. Just like the go-to compiler is the Dragon Book because it had a dragon on the cover. If you Google those, you can find them. The #1 book on compilers is, I think it's the Dragon Book, which I think is called Principles of Compilation. And then the Pelican Book is about languages, and it's by a couple of authors named Sloniger and Kurtz. And if you look them up, you will definitely find the Pelican Book. There's not very many Sloniger and Kurtz pairs running around the world. Okay, so what kind of questions are we talking about? Are the types used consistent? Have the variables been declared and initialized? What's the effect on program memory? What is the state of memory at any point in time? What previous statements might affect this statement? What do we know to be true? People, you're trying to characterize the program. Are all the variables in a defined state at this point in time? Are all the variables that I needed for this function defined? Is the entire memory structure well defined at this point in time? And then people make different semantic categories where they require all of these things to be true or something like that. There's also some interesting, we won't cover it in the class, some interesting ways that you can convert loops to Boolean statements and prove not necessarily the content of the loop body, but the loop behavior in terms of countdown can be proven in some cases that it actually is the correct number of times through the loop, things like that. All right, so let's talk about type analysis for a little bit. What's a type? Well, a type is a set of values and associated operations. When we do this class in person, that takes about 10 minutes to get to or 15 minutes to get to, because I ask you guys for input. But that's what it is, a set of values and associated operations. It's that simple. Prove me wrong. I've not seen this definition in a book anywhere. We kind of came up with it over the years. It works marvelously well. If you say something is an integer type, what have you done? You have specified the allowable values that variable or attribute can hold. And you have also specified the operations that go with that variable. If you say something is of Boolean type, you have specified the values that it can take, and you have specified the operations that are associated with it. So this works for primitive types. It also works for compound types. So if you think in the object-oriented world, remember a class was a user-defined type. Now the word value gets very fuzzy here. You'll feel comfortable with this fuzziness by the end of the semester. This is the value of a class. If a class has 5 attributes, 5 integer-based attributes, what's the value of that class? That's a weird thing to ask maybe to some people. But if you expand the term value to, oh, it's the value of each of those individual 5 attributes, all take a snapshot, and that's the value of the entire thing. It's like asking, what's the value of an array? Does an array have a value? How many of you guys think an array has a value? And I've got an array of 100 doubles. Each slot clearly has a value. Does the array have a value? What do you think? The array would be each value in it. Yeah, so the array has a value, and you can call it one value. And that value is the collection or the sequence of all the individual values in those 100 slots. And you already knew this because most of you or all of you have passed an array to a function and passed that array back. And what do functions take as input? Values. And what do they give back? Values. And I know every one of you have created or used a constructor function, and the constructor hands you back what? It hands you back an object of the class. But what do functions do? They take in values and they return values. So clearly that object is a value. We always think of, see these math people screw us up, right? They get us to think that a value is a number. When you take calculus, then they teach you that, if you're paying attention, they'll teach you that a value is an equation. And then when you take Calc 2, they teach you a value as a family of equations. So they're getting there, but they really never, I don't think they ever really use the word value with, say, a family of equations. Value is a very rubbery term. So that's the definition for type. And type analysis is there to ensure that the types are used consistently. So if you say x equals foo, well, if x is an integer, foo better return an integer. And you know this because you've all gotten, you've all been careful and made sure that your methods and functions return the correct data type. And I'm just gonna speak for myself. I regularly receive compilation errors that I screwed up and forgot what type I was dealing with, and you know, got the wrong return type for one of those things. But that's all it is. How can we do this? How can this semantic analysis be done? This is not about syntax, right? Let's go back to my whiteboard. Is this line syntactically correct? Yes. Is it semantically correct? Does it do type? Does it pass the type equivalence test? No, because x is an int, foo is a double. So there's a type error. And depending on what language you're in, that programming language or the compiler will handle it differently. Some will allow it and truncate the double. Some will just not compile it at all. Some will compile it with a warning, possible lossy conversion. But syntactically, this is a perfectly good thing to do, and semantically, it's not. And the semantics and the syntax are separate, unlike in a natural language. We can answer those two questions definitively separately. So that's the first way you do type checking, name type checking. You declare, you use a name, has to work out. Do all programming languages require explicit declaration of the variables? And or do all programming languages require that you explicitly declare the type of every variable? Which is, or what?
Definitely not the type. for some of them.
Right.
I also imagine you don't need to declare everything as well.
Right. So I know in JavaScript, you can just say var x and you don't have to say what its type is. In MATLAB, you don't even have to declare your variables at all. Is that true? I thought you could just start using them.
I think
in MATLAB you can do it
like that in Python as well.
Python? Who was talking, who was answering with MATLAB? Whoops, I'm on the wrong one.
I was answering MATLAB. If you want to
Okay.
declare it, you could just say x equals 4 and it'll.
Yeah, you can just use it, right? So since the name type checking isn't there, now what do you do? Oh, okay, so we can do structural type checking, or we can do usage-based type checking. So if I declare X, if I don't declare X and I don't have to declare its type, all I have to do is make sure that whatever I do in a particular statement or sequence of statements is consistent. And what we're asking the compiler, or usually the translator for those languages, to do is to determine the type for us based on the values that we give it. But named type checking is the most common form because most languages, the most widely used languages, I should say, Java, C, C++, require type checking. Java is actually more rigid than that. Java will guarantee the way they built their BNF structure, that they will guarantee that you will not get a type error on execution, as opposed to C. C programs will compile, but then you might get a type error on execution. Java is strict typing, as they say, and won't do that. But what about if you start to get into more sophisticated things, structural type checking? What if I have two classes that have different names, but they have the exact same memory structure? They both have 5 integer valued attributes, and they both have the same names and signatures for all their methods. They're different in name only, but in terms of memory allocation and method operation, they're actually the same. And so another form of type checking is structural type checking. Those of you that took C, you learned about structs. Was that too long ago? You've forgotten about structs? So if a struct is 1 int and 1 float, and then another struct is 1 int and 1 float, are they the same or are they different? Are they the same type or not? Well, in some languages, you may have a compiler who is clever enough to compare the structure of these compound data types and allow the equivalence. You see this most often in the object-oriented world. In fact, it was an intentional design where you use inheritance. And you say, oh, even though these classes have different names, one extends the other, and therefore I can use either. If I build all my software for the parent, it will also work for the child. Oh, and if I have multiple children, it will work for all the children. So that's not a name type checking. That's structure. Now, how do they get away with it in a language like Java? Technically, they're doing a check to make sure that you're extending. So we could argue, you could argue maybe that even though it's structural, they're using the name to actually do the analysis. The problem with that is, unless you construct your language in a very specific way, and Java there's certain things that you are not allowed to do in Java syntactically that will prevent runtime type errors. So the problem you have in general is they are not determinable in the general sense. And again, this gets back to, can I feed this program into another program and it will tell me that it's type safe or that it's type consistent? And in the general sense, no, we can't do that. That goes back to Turing. But if you restrict your language well enough, yes, you can do that. So Java, the term is strict typing. It's a strict typing system. And so Java has put so many rules on how you do typing that they can do that. But in the general sense, if you just take the rules off, and again, those of you that have taken C hopefully have experienced this, you can write syntactically correct things, you can write things that pass the semantic checks of the compiler, and then when you're executing, you still get type errors. If you're in a language like, well, the language that we're going to use in this semester, Racket, does not require that you declare types, and I promise you, you will get type errors because it's kind of hard to see the types in that particular language. JavaScript, MATLAB, you can get type errors. Okay, so if you do type analysis, you know, you can go through this and say, okay, what kind of works here? So if I look at this first box, I don't know the type, X, Y, and Z, X equals 10, Y equals 12, Z equals X plus Y. What could I fill in the blank here for the type? What do you think? Double, yeah, doubles. I think double works. Would int work? Now, that's a trick question, by the way. No. It depends on the language, right? So some languages will convert that 12.0 and truncate and assign the integer value 12. So it's a little bit of a trick question because it depends on the language. But if you have a strict language, it should not work because you're trying to assign a double to an int. So why are some languages that way? Because they recognize that they have a problem, right? They recognize that that would be a type error. And their way of dealing with the type error was to do the lossy conversion, right? The loss of the data after the decimal point. I think no is a stronger answer, but beware that, right, there are languages out there that it would work. Now, how about a string? That clearly wouldn't work. How about Boolean? Clearly wouldn't work. Now here, again, syntactically, these are all the same. I've got X equal value, Y equals value, X equals value, Y equals value. Syntactically a little different because that's a numeric value and that's a string value. Here, the only kind of type that works, maybe. Here, what type would work here? And now, again, there's a little bit of language about, yeah, so string works, right? So if dog is a string, that's pretty clear. X better be a string. And since X and Y have to be the same type, fish is a string, Y is a string. And then the only question really is string, but you can't add strings. And that's the question, Joshua, right? So are you in a programming language that allows you to add strings? If you are, this is perfectly legal. If you're in C, don't you have to use the string manipulation functions to concatenate strings? It's been close to 20 years. I think that C would not allow that, but Java allows that kind of thing. And so does JavaScript. I don't know what MATLAB does. Python does everything, so probably allows it. So depending on what language you're in, that last line is good. If you're in a language that requires that you do string concatenation via some string function, then nothing will work here. Now here, this looks bad, right? Dog and 12. There's really no type that should work there. If a language allows that, I would argue that we should never ever use that language. Although I think JavaScript might actually let you get away with that. I'm not sure. What some languages do to try to resolve it, they say, okay, X is a string, Y is a numeric value. I'm going to convert it to a string, and then I'm going to do the concatenation. By the way, I'll do that last. Remind me to go back to that. And then what's this one? I can't. What do I do here? What types are allowable? I don't know what the user is going to give me. Now, hopefully I'll tell the user what to give me, right? But you know how those users are. You can't rely on them. Is there a type that would work for all possible user inputs here? Not really. Now, if we say that it's int, hopefully the user gives us 2 ints. If we say it's double, hopefully the user gives us 2 doubles. If we say it's string, hopefully the user gives us 2 strings. But, you know, this is a problem from a semantic analysis, right? How do I do type checking if I don't even know what's happening yet? Well, think about how Java fixes that. So let's talk about ways that Java gets around this problem. It's not just x equals. Did I get that right? So Java actually specifies, look, I'm only going to accept an integer value. Now you've constrained the user. Java, the nature of the language has. By the way, this whole thing of concatenating strings with the plus sign, how does that make any sense? This is a string and this is, let's say, a double. How does that make any sense? What's Java doing? Messing with your head? Exactly. So what Java does is everything that you input in there, if it's already a string, it leaves it alone. If it's not a string, it runs the string conversion. You know, there's a double to string conversion. There's an integer to string conversion. And so it converts everything to string and then does the plus operator to concatenate all the strings that you put in there. Right. So I'm not sure if it's a true cast, Casey. I think it might actually be an actual conversion because that may have some slight more sophistication than a cast. But your answer is effectively right on the money in terms of what the effect is. Okay, I need to get this back to where it was, or I'll never forget, right? I wouldn't forget that. Okay. All right. So this is some idea of the kinds of analysis that's going on. Notice these were all syntactically correct statements, I believe. Other than putting type question mark, they're syntactically correct. So what kinds of analyses are there? We'll talk briefly. Again, this is very brief about these things. 3 main semantic forms: denotational, operational, axiomatic. And I'll talk about denotational today and then operational and axiomatic on Wednesday. And again, I'm giving you some book chapters, but the book chapters are there, you know, for your amusement and enjoyment. But the level that we're looking at here is that you guys can at least provide a one-liner definition of what, say, denotational is, operational, axiomatic, and that you have a basic and foggy idea of how it works. The denotational semantics are describing program behavior in mathematical terms. By that, I mean they truly see this as a math function, math operations. Now, I guess we can get all philosophical that, you know, Boolean is math and operational is math too, because it's a logical branch. That's all fine. I'm saying in the heart and soul of mathematics, the way we think of it in a discrete structures way. And the idea here is they have the central notion of a program store. And the reason they have a central notion of a program store is because it serves as the math model for memory. And if they had a real world model for memory, then they would be tied down to, say, a particular programming language paradigm like imperative. Whereas, you know, functional doesn't really have the notion of a program of memory, and object-oriented, you don't really know what's going on in memory all that much. So instead, it's abstracted away. The program store, this is the abstracted form of memory, and it's basically at any point in time you have variable value pairing. So the whole memory is nothing more than a set of variable value pairs. And at any point in time, you can look at, here's the program store, here's all the variable value pairs. And again, value is going to be a rubbery word. We're going to treat it as just simple numeric values for here, but it is a rubbery word. Then the idea is the meaning of the program is, again, input, output, observable input, output behavior. So the meaning of a program is the transformation that the program imposes on a store. So I give the program an input store, it does its thing, and then I have an output store at the end. And that transformation, that input, output behavior is the definition of the program behavior. Now, if you think about it, only assignment statements can make changes to the store. And if then else can't, except that an if then else can contain assignment statements. And I think we talked about this before. Is if then else one statement or more than one? And the answer is yes. It's one statement that happens to contain more than one. So you have these recursive rules that you can develop in the denotational semantics about what is the effect of executing this statement. Now, all of the rules for the denotational semantics is based on single statement. And as you recall, in order to do program behavior, fully Turing computable program behavior, you only need 5 kinds of program statements. You need a declaration / initialization. You need assignment. You need some form of repetition, like a for loop or a while loop or recursion. You need some form of selection, like an if then else. And you need I/O. Now, we're not going to be concerned with I/O here because we're only worried about the computational aspects of the program, not the physical nature of getting input and output, but the fact that an input store magically exists and an output store magically exists. So if you develop the denotational rules for each of those statements, you've got the rules for an entire notional language. How do you get a program out of that, though? Well, a program is nothing more than one statement after another. If a program is one statement after another, then all we need to do is make a rule for how we can do sequence. How can we get 2 statements together? So if I had a rule for, okay, here's the rule for your assignment. The assignment statement updates the store in this fashion. Then the rule would be, oh, program sequences looks like this. I evaluate S2, the second statement, based on the store that S1 gave me. So S1 has some kind of a store at its beginning. It performs an operation, it makes a new store, and it hands that store to S2. So once you make that leap from one statement to 2, now you can do the denotational semantics of an entire program. Why do people put themselves through this? By the way, if you ever want to get rid of somebody like an insurance salesman or something like that, just start talking denotational semantics and show the notation and they'll run away. I'm going to run through assignment statement really quick, and no, I'm going to save it for next lecture. We'll go back over that last slide on Wednesday and go through the rough form of denotational semantics, and then go through the rough form of the operational and axiomatic also. Again, the idea is to give you an idea of how these things work. Okay, if you have questions about anything, throw me a message in Canvas or put it on the discussion page. I do check those much more than I check the, wait a minute. Then I check my mail. So please use Canvas to contact me for the course. All right. Bye, guys.